Hello guys, today I'm going to teach you how to formulate the equation of motion by two methods, which are uh, Newton's equation of motion, which is equal to which is F equal to ma, and another method called the Lagrangian method. The Lagrangian method is stated as this. It is based on kinetic energy potential energy and dissipative energy. So we are going to look at these two methods in order to formulate the equation of motion for a spring mass system, which I will represent as this. I have a block of mass m, which is supported by a spring with spring stiffness K and a damper whose damping coefficient C. And this system is not fixed. It means it can bounce at the ground. So this system has a one vertical motion, then we call it Z, and another vertical motion at the ground, then we call it R. Then I will start with Newton's equation of motion to formulate the equation of motion for this system. With Newton's equation, we first draw the free body diagram. In our case, we have one mass. So our mass has a vertical force which is equal to mass times the acceleration. In our case, the acceleration is z2 dot, or second derivative of z with respect to time. Then we have two downward force, which are Fd, the damping force, and Fk, the stiffness force. The expression of these two forces, Fk, which is the spring force, is equal to the negative spring stiffness times the displacement. In our case, the displacement is Z minus ala. Fd, which is dissipative force or damping force, is the negative of c times the velocity. So at this stage, we have to calculate or apply the equilibrium principle, which states that the summation of force around the point, a fixed point, must be equal to 0. In our case, the mass times z dot 2 dot must be equal to Fk plus Fd, or mz dot is equal to minus k z minus r minus c z dot minus r dot, or in the simplified form, mz2 dot plus cz dot plus kz is equal to cz cr dot plus k ala, all we have mass times z2 dot plus c z dot plus k z which is equal to force, where the force equal to cr dot plus k r. So we are done with the Newton's principle, Newton's formula to formulate the equation of motion for mass spring damper system. So we can move on the second method, which is Lagrangian method. Lagrangian method. The Lagrangian method is formulated like this. It is stated that the partial derivative of kinetic energy with respect to the axis. In our case, the axis is z minus the first derivative or partial derivative of the kinetic energy with respect to z plus the partial derivative of potential energy with respect to z plus the first derivative of dissipative energy with respect to z dot must be equal to 0. So our duty is to formulate the expression for all these energy. First, let's look at the kinetic energy. The kinetic energy is directly proportional to the velocity squared over 2, or a half of mass times velocity squared. Velocity squared in our case is z dot squared. In our system you have only one mass, so nothing else. The potential energy V is equal to a half times K, or stiffness coefficient, times displacement squared, which is z minus r squared, or equal to a half z squared minus 2zr plus r squared k. The dissipative energy D is equal to a half damping coefficient z dot minus r dot squared of a half z dot squared minus 2z dot r dot plus r dot squared times c. So let's calculate this first derivative. Derivative of k with respect to z dot is equal to mz dot. As well, the first derivative of kinetic energy with respect to z is 0, and the first derivative with respect to time, or the first derivative of k with respect to z dot is equal to mz dot. Then we have to perform the first derivative of potential energy V with respect to Z, which is equal to a half times 2Z minus 2R plus 0 times K, which is equal to K Z minus R. The first derivative of dissipative energy with respect to Z dot is equal to a half times 2Z dot minus 2R dot plus 0 times C, or is equal to C Z dot minus R dot. So let's put this expression into the general formula for Lagrangian principle, or this one we have here. We have to replace everything by their own values. So first, we have mz dot, then minus 0, because this expression is 0, this one is 0, this one, the next one is k z minus r, the next one, which is the dissipative energy, is this value. So c z dot minus r dot, which is equal to 0, or mz dot plus k z minus r plus c z dot r dot is 0, or simply mz double dot plus k z dot is equal to c r dot plus k r, which is the same expression as the one we have before. As you can see, both methods are easy to use for formulating the equation of motion for a dynamic system. So, thank you very much. See you next time in programming.